In mathematics, we spend a lot of time working with expressions. And expressions are made up of constants, which are static values, and these are typically like numbers, symbols that stand for numbers like pi 3.1415, or technically operations, but they're just a number as a result. So the square root of 2 is 1.414, and it continues. In addition to constants, we also have variables. These are changing values or varying values. And normally we use the alphabet like X and Y. Um, we can also use different alphabets, like the Greek alphabet. Alpha and epsilon are common variables we can use in mathematics. Let's consider these two expressions here. In the first expression, we have three things separated by a plus and a minus. This thing, and this one. These are all called terms. Terms are these kind of like single units inside a expression. In fact, terms are themselves expressions nested inside of expressions. And in the second expression, we have two terms, this first one and the 12. And the reason why we have two terms and not like 2 and 3x, 3x and 4 is because those things are locked within parentheses, and the parentheses are multiplying. And these things are actually what are called factors. Factors are separated by multiplication and division. So within this first expression, inside this first term, we have 3x, y to the 7, and z. These are all factors within this term. We also have 2a and b, and then 16.5 n and m. Those are all factors within their respective terms. Inside the second expression, we have two factors, this factor 2 plus 3x, and this factor 3x minus 4. Of course, these two factors, have within them two terms, and those are separated by the plus and minus inside the factor. So we have a term within a factor within a term within this overall expression. And of course, 12 is a term. It's also its own factor. I can write 12 as 12 times 1. So 12 is a factor in its own right. With expressions, we can solve them if we know what the variables are. Otherwise, we combine like terms. And that's the only things we can do with expressions when it's just a simple expression given. So solving an expression, we're going to use order of operations, but combining like terms, when combining like terms, we need to keep in mind the distributive law. This is just where you have some number multiplying a quantity. That means that you can distribute this number over that quantity. And it's important to note that the distributive law only applies for multiplication over addition. Multiplication distributes over addition, not over multiplication or division or anything like that. So A times B times C does not equal AB times AC. It's not over multiplication, only addition. And because it's addition, that means it's also subtraction. So keep that in mind for the distributive law. Now, solving expressions is done using order of operations. Hopefully you've worked with this before. You may have heard of PEMDAS. A better way of thinking about it is called GEMA. GEMA stands for grouping. There's a lot more grouping symbols than just parentheses. Parentheses are, of course, a grouping symbol, but you can also have brackets. You can see curly braces. You can see absolute values, which we'll talk about later on. Something like a radical symbol or like a square root, cube root, things like that. Those are also count as grouping symbols. and also the fraction bar. So if I had a over b, or I should say something like a plus b over c plus d, this fraction bar groups the top and the bottom together. So there's lots of grouping symbols that we understand in mathematics that we have to do first before we can do anything else. Exponents are, of course, what you think of it. 2 squared equals 2 times 2, so 4. Multiplication and division, these are happen at the same time. So division is the same thing as multiplication. That's why they happen at the same time. Gima just makes it clear that we're assuming they're the same thing, right? If I wrote a divided by b, that's the same thing as a times 1 over b. It's just multiplication by a reciprocal. Addition and subtraction are done at the same time. Again, they're really the same operation. A minus b is the same thing as a plus a negative b. It's adding by a inverse, or an opposite sign thing. Okay. For these two expressions, we know what the variables are. So in this case, we know what x equals 7. So we're just going to plug 7 into the expression and solve the expression. So solving for it, we're just going to use order of operations, get a simple or a single number as a result. Order of operations is Gima first, grouping is first. There's only one grouping symbol in here, and that's the parentheses. 7 plus 3 is done first, that is 10. Now, I kept the parentheses here, but I can actually drop the parentheses at this point. They don't actually mean anything when there's only a single number on the inside. It's all about clarity. You can write parentheses in there if it's more clear to you. But here I can drop them and replace it with the multiplication, and the clarity is still there. The next thing we do is exponents. 10 cubed is going to be 10 times 10 times 10, or 1,000. Next is multiplication and division. That's just 2,000. And then finally, addition and subtraction, 2001. So that is the answer, or the solving of that expression. Okay, for the next one, we have b. B we can plug into this expression and simplify. So we have negative 11 plus 3 times 5 plus, whenever you plug something in, plug it in parentheses, because that tends to make it a little bit clearer what's happening. Sometimes things can get confusing. For instance, if I didn't plug in the b in the bottom with parentheses around it, you may incorrectly do the negative of 2 squared, which would be negative 4. Here we have negative 2 squared, which is negative 2 times negative 2, which is positive 4. So it's a good idea to always input things in parentheses whenever you're doing that. Okay, now order of operations needs to be done at the same time, but once you start understanding how the process works, you can do them at different paces. So for instance, here I have a plus in between this square root and this fraction. That means, because addition is done at the very end, that means that everything I do in the square root and everything I do in the fraction must be done first. The entire simplification must be done first before anything can interact between the square root thing and the fractional thing. So I can go ahead and work on this grouping symbol. This square root groups the what's inside of it, and the fractions also group everything on the inside. So I need to deal with the square root thing first here. I can do multiplication before addition. So this is not done first. The multiplication is done first. 3 times 5. That's 15. In the fraction, I have negative 2 plus 5. That has to be done before anything I can do with the fraction, because the fraction bar groups everything in the numerator and everything in the denominator. So before I can do anything between the numerator and the denominator, I must simplify them. So I can do -2 plus 5 first on top. That's going to give me 3 cubed. And on bottom, we have this power, -2 squared. That's 4. Okay. Let me make some kind of, marker here since I didn't give myself enough room. I can simplify this up underneath the square root. Again, there's no interaction between these two things, so I might as well simplify that. -11 plus 15 is 4. And I do still have to get rid of or simplify the numerator completely. 3 cubed is 27. And on bottom here, we have 4 minus 15. That's -11. And so you can see I'm doing different steps of order of operations in different kind of ordering, but they're not really in different ordering. I'm always following grouping, exponents, multiplication, and addition. I'm just doing it at different, each portion of the expression in different stages because I can. I can save time that way. Okay, this fraction cannot simplify, so I'm actually going to leave it the way it is. And I'm going to simplify the square root. The square root of 4 is 2. So we get 2 plus 27 over -11. I can actually bring this negative out in front because the negative on a fraction can move to the top or the bottom. 27 over -11 is the same thing as -27 over 11, which is the same thing as -27 over +11. You can move it around because everything that's happening in this fraction is multiplying or dividing. And a -1 multiplying or dividing anywhere will always be -1. So what I can do is I can actually move it out in front, and that interacts with this plus to make it a negative. At this point, I can combine these two things. I just need to have common denominators, so I'm going to multiply by 11 over 11. That's 22 over 11 minus 27 over 11. And that, of course, gives me a final answer of -5 over 11. You can write that as a decimal, but I'm going to leave it as a fraction. I think it's cleaner that way. So give this a try in number 1. Okay, with these two expressions, we do not know what the variable is, so the best we can do is combine like terms. And combining like terms, you need to have the exact same variable part. So for this first one, I'm going to look at the variable portion, not the number in front. The number in front doesn't matter. It's just about the variable. So here I have z cubed, and here I have z. And so I'm going to mark it differently. I'm going to mark it with two lines, for instance. I could also give it a different color, like I could do red instead. Here I have 7, so that's a different color again. I have z cubed again, so that's going to be the same color, black. Or if it helps, you can mark it with different lines, so like straight lines, double straight line, curvy line. Z squared, I can do it with green here. I can do double squiggly line like that. Then I have z, so red. Z squared, that's green squiggly. Then z is red. And finally, the last one is the blue squiggly. Okay. And now all I'm doing is I can do this a couple ways. You don't have to do the rewriting portion. I'll do it here just to show you how it's done, but you can save yourself some time by just combining the like terms that are like terms. So I'm going to rearrange this so that each one is right next to each other. So that means that this one and this one, I'm going to write it as 6z cubed minus 3z cubed. Make sure you leave the sign in front of the term and move it around. You can do this because addition and subtraction is commutative, meaning it can move around in an expression. Okay, now I'm going to work on these double bars, the red ones here with 2z. So it's going to be plus 2z. Then we have this one here, plus z. And finally this one here, plus 5z. And so I'm going to kind of simplify this a little bit by just crossing them off to making sure I got I took care of them all. Now we have this 7 here, so a negative 7 minus 4. And finally, I'm kind of going way too far out, but these are the final two, plus 2z and minus 2z squared. Okay, now I can combine these two like terms. If you have the same exact variable part, all you have to do to combine them is add or subtract the numbers in front. So here we have 6z cubed minus 3z cubed. So we have 6 of them minus 3 of them. That means there's 3 left. And leave the variable part the exact same. Here we have 2z plus 1z, right? I can write this as 1z, plus 5 more. So 2 plus 1 plus 5, that's 8 total. Here we have negative 7 minus 4. That's going to be negative 11. And plus 2z minus 2z, those cancel. I'm just going to get rid of them like that. There are no like terms that I can combine any further. If there were, I would need to combine the like terms again until there are no like terms. I have a z cubed term, a z term, and a no variable term here. So that's completely combined. Okay, for this next one, we need to get rid of parentheses. They kind of lock everything in it. So I'm going to work on the innermost set of parentheses. First, we have 6 times x squared is 6x squared. 6 times negative 1 is negative 6. Okay, now I can get rid of these parentheses by distributing the 2. 2 times x is 2x. 2 times 6x squared, you're going to multiply the numbers. 2 times 6 is 12. The variable stays the same. 2 times negative 6 is negative 12. And then we have plus 3x squared minus 5x. And now I can combine like terms. I'm going to show you how I would do this normally. I see I have x squared and x squared. 12 plus 3 is 15x squared. Okay, those are done. Now I have 2x and minus 5x. 2 minus 5 is negative 3x. Okay, those are done. And I only have negative 12. So that stays. And as you can see, there are, I've used up all of the terms. I've crossed them all off because I used them. And there are no like terms in the answer. So that's how I would tend to go about it in my actual doing the mathematics. Give it a try in number 2. Okay, let's look at a case study here, and we're looking at cost of tuition for Wiregrass. And if you follow this link, you'll be brought to this screen here. And in this screen, you can click on current tuition and fee schedule, and that'll bring you to this document here that lays out the tuition that you'll be billed for any semester. And as you can see, there's a lot of different lines here. The main thing is that the credit hours is changing in this first column, and therefore tuition is changing. And all the rest of the columns here, except for this total, of course, they're always the same. So you always have a flat registration fee, a flat accident insurance fee, activity, tech, facilities, instructional printing, and campus safety fees. And so what we can do is we can use this information to write an expression that models this behavior, a mathematical expression that kind of fits with the same. That's what's called a model. And I can do that by looking at, well, if registration, accident insurance, activity, tech, all these things are always the same, all I have to do is just add these things all up. Now the tuition, if we have X credit hours, or I should say T credit hours, I think T is more natural since it's a time, then it's at $100 per credit hour. That means that the cost is 100 times your credit hours, so 100 times T. Okay, so T is going to be our credit hours. And our tuition cost is going to be $100 per credit hour. If we have T credit hours, that means it's 100 times T. That's our tuition cost. And then we're going to add on each of the individual ones. So the first one, I believe, was the registration cost at $62, accident insurance at $6, and then I'm going to continue on with the rest of it. Okay, and these are all the fees that are listed. And so there's no real reason to have an expression that looks like this because we have a bunch of like terms. All of these things do not depend upon the hours, they're just a flat rate. And so all of these are just numbers. So we can combine them, and adding them all up, we get $381. So now what we can do is we can test this thing out. Since the last column in the document had the costs, we can actually test it to see if we have an accurate model for this situation. So let's say we took 8 credit hours. Let's plug in 8 into there. So when t equals 8, we just plug it into our expression. 100 times 8 is 800. We have to do that first by order of operations. And then we can add these two together. That's going to give us 1181. Going back to the document, you can see here at 8 credit hours, go all the way over to the thing, we get 1181 total tuition and fees. So that accurately, or that does fit the data. The only issue with our model is that this is a continual thing. So if we took, for instance, 30 credit hours, so if t equal to 30, you would plug in 100 times 30 plus 381. That's going to give us 3,000 plus 381, or 3381. And this is actually incorrect. So in the fee schedule, you can see that 15 plus, anything more than 15, or 15 and higher, I should say, anything that's 15 or higher will always be $1,500 in tuition, and therefore will always be 1881. So whenever you're translating these kind of situations into mathematics, make sure you put the bounds in there, because the bounds are very important when you're translating back into the real scenario. So 30 hours, if t is 30, it's only going to be 1881 and not that 33 that we found, $3,300 that we found.